A quick new idea, daily, from the world's greatest TEDx talks. I'm your host, Atossa Leoni, and this is TEDx Shorts. Have you ever wondered, if human beings ever live on another planet, what will they eat? Sarah Kessans is a biochemist who says the future of interplanetary travel will depend on our ability to make food and medicine in this new world. Today, she explains how synthetic biology might be our key to doing this.
It won't be long before we become a multiplanetary species. It's in our human nature to explore. Just as our ancestors developed the tools and the social skills to venture beyond the savannah to populate the entire globe, we're now developing technology that will transport us beyond Earth. But the technology that we create to get us to Mars won't be of any use to us if we can't find a way to feed ourselves once we get there. It'll be nearly impossible to transport all the food we need from Earth to our new home. We're going to have to figure out a way to produce our food once we get there, using the resources found on Mars. We call this in situ resource utilization, or ISRU. The basic ingredients we'll need include CO2 and other gases from the atmosphere, water from frozen deposits found on the planet, and minerals and salts from the Martian soils and rocks. Unfortunately, Martian soils aren't really conducive to agriculture. They're full of heavy metals, and they're saturated with perchlorates, which are water-soluble, chlorine-based molecules that are toxic to humans and many of the things that we'd like to grow. We're going to either need to figure out a way to remove these toxic compounds or to engineer organisms that can thrive in non-ideal, resource-limited environments. I'm currently working at the University of Canterbury in a fantastic collaboration with Callahan Innovation, Massey University, and Victoria University of Wellington. We developed a powerful new synthetic biology tool for assembling large biosynthetic pathways. Our system is called midas, which stands for Modular Idempotent DNA Assembly System. In short, midas allows us to combine dozens of genetic parts into a single piece of DNA. Although there are other DNA assembly systems out there, midas is unique in several ways. First, midas allows us to assemble DNA seamlessly, without leaving in extra bits of DNA that can interfere with downstream applications. And midas gives users complete control over the gene order, orientation, and direction of DNA assembly. And this allows for fully customized biosynthetic pathways. And midas is simple. With just a few design rules and our suite of DNA vectors, anyone can quickly and efficiently assemble biosynthetic pathways. Our system starts with a library of small, reusable bits of DNA. These bits of DNA include the genes themselves, as well as bits of DNA that can turn genes on and then regulate how they do their jobs. We can choose from as many or as few bits of DNA as we need in order to get a complete set of genetic instructions in a pathway. Then we throw these little bits of DNA into one big pot, or in this case, a tiny tube, with some enzymes that recognize specific sequences in our DNA. From there, those enzymes act like very precise scissors and glue for cutting and pasting our DNA. In just a few steps, midas can turn lots of little bits of DNA into a functioning biosynthetic pathway. This gives us the ability to mix and match individual genes to create new biosynthetic pathways. These new biosynthetic pathways that can then be engineered into a variety of organisms, from bacteria and yeast to fungi and plants. So far, we've used midas to assemble tens of thousands of letters of genetic code into discrete pathways. The pathways that we assemble can be used to synthesize molecules that can be used as antibiotics, insecticides, anti-cancer drugs, and other pharmaceuticals and agriculturally valuable compounds. We're currently putting these pathways into simple lab-based organisms like filamentous fungi, which are similar to the mold that grows on your bread. Using these fungi, we're now developing methods to produce large-scale volumes of high-value compounds that we couldn't produce with traditional methods of chemical synthesis. With midas, we can turn mold into gold. But midas is not limited to lab-based organisms used to produce industrial chemicals. Midas can also be used to design and engineer new food organisms for Mars. To start our Martian colonies, we're probably going to have to engineer our organisms on Earth first, and then fly initial stocks of them there. We've got some great starting materials in naturally occurring algae, yeast, bacteria, and fungi. In fact, we're already using many of these microbes in our current foods and pharmaceuticals. For example, we use yeast both to ferment the sugars in malt into alcohol and to provide the base of our favorite Marmite spread. We use bacteria to make yogurt and to produce life-saving insulin. We eat fungi in the form of mushrooms and use them to synthesize cholesterol-lowering statins. And the diversity of organisms found throughout the globe contain libraries of genetic information. The biosynthetic pathways contained in those libraries can be used to synthesize new flavors, nutrients, and textures into new food organisms. One of the first organisms we'll use will be cyanobacteria. We already eat cyanobacteria in the form of spirulina, which is made from the dried cultures of cyanobacteria. In addition to being nutritionally balanced, cyanobacteria can also thrive using the most minimal of resources. Cyanobacteria can turn carbon dioxide, a few mineral salts, water, and sunlight into a soup full of sugars, proteins, fats, and essential vitamins. We can then take this soup, dry it down, and harvest it, and use it as food itself. Or we can also use it to feed other simple and small organisms that can't photosynthesize, like yeast, bacteria, and fungi. So why go through all the trouble of engineering these organisms when we could just use them as they are? First, the food that we produce on Mars will need to satisfy all of our nutritional requirements to keep us physically healthy. On Earth, we can choose from a wide variety of foods to get that balance right. But we won't have that variety on Mars. We'll only have access to a few simple organisms. Getting them to provide everything we need is going to take some engineering. But food is more than simply filling our bellies. We also need to think about our human psychological needs. Tasteless algae paste may satisfy our calorie and nutrient requirements, but imagine eating only that for the rest of your life. It's enough to make even the most hardcore adventurer question the decision to move millions of miles from the nearest takeaway shop. As astronauts on the International Space Station can tell you, quality and diversity of food are really important for mental health. Eating the same mushy, rehydrated meals again and again for months on end can be soul-destroying. Pizza night on Earth is pretty great, but pizza night on the ISS is even better. Making delicious food with our friends makes us feel good and brings us closer to them. And the same will be true on Mars, where missions will extend long past the current ISS mission timelines. So how exactly do we go about designing food that can satisfy all of our needs from simple organisms? Let's go back to our example of ketchup. Ketchup is not going to form the basis of the majority of our calories on Mars, but its ability to boost the flavor of our food and the morale of our Martian comrades is invaluable. Let's think about the traditional ingredients that go into making ketchup. We've got tomatoes, onions, garlic, sugar, salt, vinegar, and spices. Growing tomatoes and onions via hydroponics and aeroponics on Mars will be quite resource intensive. And much of that energy will go into making the inedible stems and leaves of the plants. And what about spices? How do we grow peppercorns and cloves on Mars? But we don't need whole tomatoes, onions, peppercorns, or cloves. Really, we just want the biomass and the flavors that they provide. This is where synthetic biology comes in. What if, instead of all the inefficient growing and processing of whole plants using the limited resources on the red planet, we could produce all of those ingredients using one resource-efficient organism? Using midas, we could assemble the various biosynthetic pathways to produce different flavors. For example, we could engineer and then assemble the biosynthetic pathways for the production of lycopene and associated carotenoids that give tomatoes their flavor. We could then introduce additional biosynthetic pathways to produce allicin. We could also introduce the biosynthetic pathways for the production of capsaicin and piperine to add a bit of spice. Then we could give the algae the genetic instructions for increasing the cellular sugar content. And at the end of the algae's life cycle, we could turn on a pathway for producing a little bit of acetic acid. With this designer algae, we'd simply throw a starter culture into some salt water and give it some sunlight to grow. A week or so later, we'd strain out the water, and boom, we've got ketchup. While this might seem like science fiction, I'm currently working on projects that will make this space ketchup a reality. In the same manner, we'll be able to engineer a variety of organisms that will provide a diversity of flavors, nutrients, and textures. We'll be able to make a cornucopia of ingredients that can be used as is with minimal processing.
The TEDx talk you just listened to was recorded at a TEDx event in Christchurch, New Zealand. All TEDx events are independently organized by volunteers who believe in TED's mission of ideas worth spreading. Special thanks to the organizing team at TEDxChristchurch. Want to listen to the full talk? Find Sarah's talk and more at ted.com/TEDxShorts. I'm Atossa Leoni. Thanks for listening, and see you next time.